Hey, it's a flashback lecture. It's like we're back in COVID. Well, I guess I'm back in COVID. So we're going to run through the rest of these palladium cross-coupling reactions and Heck reactions and stuff. Hopefully I don't have to stop and start too much because every time I do, I'm going to have to edit everything together, and that's going to suck. So we left off right down here. We were talking about the after the migratory insertion, we were talking about the beta hydride elimination. So if I can draw this correctly, over here on the next slide, we will see that now I'm vamping, stalling for time because I did not plan this well enough ahead. Okay, so we've got our palladium with our halide and our ligands on it, however many ligands we have. We've got our R group back, our R1 group is forward. We've got our aromatic group. I'm just going to put phenyl here. That is the group that we just added. And then we've got this like this. All right. So we had talked about before that the palladium and the phenyl group that you add get added to the same side of the double bond because the palladium is actually holding on to the phenyl group. So they have to be on the same side because they were connected together before they bonded to the double bond, and they approached the double bond from the same side. Now, for palladium to leave this structure, it has to take a hydride with it. So it does a beta hydride elimination. I'm going to try to make this handwriting legible. All right. And beta hydride elimination is a syn elimination, meaning that the palladium and the hydrogen that are leaving have to be on the same side. They have to be lined up. So for that to happen in this example, I have to rotate around that bond. So again, my patent pending twisty arrow, and you're going to have the palladium and the hydrogen now on the same side. So the carbon with the palladium in this example is going to stay unchanged, and we rotated this group back here. So the hydrogen came up, that moved R2 forward, and that moved the phenyl back. And you can check the slide that I didn't mess it up. I did not mess it up. So now at this point, the hydride, basically electrons from the hydrogen, from the hydride, go to the palladium. The electrons in the carbon-palladium bond come down, and that is going to make your double bond that you wanted. It's going to make your product. Now, if you look, R and phenyl are on the same side of this structure, so R and phenyl are going to be on the same side of the double bond, and then R1 and R2 are on the same side, so that is going to put R1 and R2 on the same side. Right, and now what does this leave you with? This leaves you get your product, plus you get palladium HXLN. Right, so you have this palladium that is stuck between an acid. Right, it's the H and whatever is this, halide or halide-like thing, bromine, iodide, chlorine, triflate, right? So you can think of this next step as happening kind of one of two ways. You can either A, think of it as the base helping to, that's a really bad lone pair, let's try that again. So you can think of the base kind of coming to help grab the hydrogen and push off the halide to get you back to your palladium 0 with your ligands around it, plus base H is positive, plus X minus. Or you can think of it as the palladium does effectively another reductive elimination, right? Where the palladium will remove, go over here. So, might as well do it here. So palladium could do a reductive elimination to make your palladium 0 with your ligand plus your HX, and then HX reacts with the base to make the salt. So the base's only role in this reaction is to soak up any acid that is made during the course of this reaction. So that's kind of the whole catalytic cycle. If we go back here, right? So you get your product over here. You have your palladium with the acid on it. Do a reductive elimination, either facilitated by or either facilitated by the base or just the base being there to react with the acid that you generate here, right? Because you can't have a whole bunch of acid building up, as it could react with your double bond, and it could also react with your palladium and put your palladium in the wrong oxidation state, right? We need the palladium to be palladium 0, and if we just leave all this acid around, that palladium can become palladium 2 more easily. All right, so let's look at some examples. I put a bunch of slides in, so like don't think you're having like a stroke as you just see like little gray lines fly by. I tried to put some slides in between things so that I didn't have to like pause the recording. So you'll just have to deal. So if we look here, this carbon right here is this carbon. Is this carbon right there, and then this carbon here. Why does it keep doing that? Is this carbon here? Oh, this is annoying. Is this carbon here? Right. So when this happens, so this is something to kind of note with the beta hydride elimination, is you can kind of determine where your double bond is going to be formed after your Heck reaction based on the structure of your starting double bond and the structure of the product that you're expecting. So if we look here, right, this double bond right here, when we react with it, we're going to just draw it up here. We'll draw like a shortened version, right? So we're going to have the palladium with our ligand, and then we're going to have our hydrogen here. And so the only place, so here's our aromatic ring, to give you a little bit more, a few more road marks or landmarks on like what you're looking at here. And then here's our, one of these is our mom group, right? Oh no, the mom group kind of goes away. Where did our mom group go? I think I lost the mom group. Oh, the mom group's here. Gosh, I apologize. All right, there's the mom group. That's why I was confused. All right, so there's our aromatic ring. So now when we go to do the beta hydride elimination, there's only one hydrogen that can be eliminated. So we know exactly where the double bond's going to go. It's going to end up making the double bond back by removing this hydrogen to make this double bond that is beside the aromatic ring. Now in this next example, we have a tri-substituted double bond. right? Right here. Might be a little hard to see. Right, so we've got that double bond. And then when we add our palladium, we make our new bond. We have our palladium, this, and then we have our new bond, our little aromatic, which is just what I'm going to call this guy here. That's our aromatic group. Now, there's no hydrogen here, right? This carbon right here has no hydrogen on it. So I can't beta hydride eliminate in that direction. The only thing I'm able to do is beta hydride eliminate towards this methyl group here. And that's why you end up with this double bond sticking off the end like that. Because the only thing that you can do is beta hydride eliminate that way. So one thing that you can do with Heck reactions is, let's say, I'm gonna do like a generic one. I think this is similar to your homework, right? But imagine, if you will, you have something that looks like this, like a bromine or whatever, and you do a Heck reaction, right? So I make the oh no, that's the wrong spot. I make the product, maybe. I make the product. I can't. Okay. It's been a while since I've had to do this. I'm trying to remember everything. So I can get to this, right, where I have my palladium on that carbon, but now there is nothing, there's no hydrogen to do beta hydride elimination with. So now what you can do is you can add more reagents. Oops. You can add other reagents to trap this palladium. So you could add like CO2, and you could make a carboxylic acid where that CO2 gets added and replaces the palladium. You could also add some metals to do palladium cross-coupling reactions, right? Because now you have a palladium on a carbon. Now you can maybe do cross-coupling reactions. So you could use CO2. You could, so this is use CO2. You could use, let's say a tin, right? And you could do a cross-coupling. Right, and that'll give you a cross-coupling. So there's a bunch of things you can do if you have your palladium trapped and it can't do a beta hydride elimination. It's just stuck there waiting on you to give it some reagent so it can get off that and turn the catalytic cycle over, hopefully. So those are kind of your Heck reactions. Oh, I guess I only did, I did both examples. All right, so we're going to talk about palladium cross-couplings now. So palladium cross-couplings, right, are when you take two things. So we were kind of generically before, you have an aryl halide, you have an aryl or an sp2 hybridized halide, and then a metal or metalloid. So I should specify here, this is sp2, sp2, right? And then you add palladium, and then you stick those two things together. So this carbon here is that carbon there, and this carbon here is this carbon here. Right. Now, it doesn't always have to be an sp2 hybridized halide or sp2 hybridized, what's it called? metal or metalloid, the vast majority of the time they are sp2 hybridized, but not always. And I just realized I was kind of turning away from my computer, so I don't know how well you were hearing me. So I'm going to reorganize myself real quick. Hopefully you heard me this for a few minutes. And then, so it's not always sp2, but mainly they're sp2. We're going to see a few examples that have sp3 hybridized halides or metals, right? And then, while they all have different names, right? We kind of went over those. The mechanisms are pretty much the same. The only thing that changes is what the metal is that's being used. But the mechanism itself pretty much stays the same. So, kind of the generic catalytic cycle is the same thing that we saw before, right? You either start with palladium 0, or you make the palladium 0 in the reaction from palladium 2, where the palladium 2 reacts with typically some sort of trialkyl phosphine and gets reduced from palladium 2 to palladium 0. And then once that happens, you get some ligands around that palladium. Now, thankfully, the first step of a cross-coupling reaction is the same as the first step of a palladium of a Heck reaction, where you have your palladium doing oxidative insertion and sticking itself into the carbon-halogen bond and going from palladium 0 to palladium 2. So that is the same first step for both. Now, for let's see if I can get all these here. Stilly, I'm gonna like act confident like I was gonna spell Kumata correctly, but we're just gonna we're gonna go check. Kumata, and then Negishi coupling, another thing that I was going to confidently try to spell here. Right. The next step is a transmetallation, where you swap the metal on your whatever your R metal is for the palladium. So you're transmetallating. You're going from tin, magnesium, or zinc to palladium. So let's say you've got your, make it look the same here. You've got your palladium with your X and your ligand. And then you've got, we'll make it a double bond so it looks different. So you have your tributyl tin, right? So what transmetallation is, again, trying really hard to make it so you guys can read stuff. If you hear Gavin screaming downstairs, he is sick, and the only way he knows how to handle it is to lash out and make everyone's life as miserable as his. So transmetallation, you are swapping the metal on this carbon. So you're swapping this tin for the palladium. So you end up with palladium that plus you put the halide on that metal. So you don't need base in these because you never make acid. You just put the halide on the metal, and that compound is relatively inert to these reaction conditions, so you don't have to do anything like sop up anything, right? You don't have to worry about, oh, I'm making acid, it's going to mess with my palladium. No, none of that is necessary. It's just fun. So that's your transmetallation. And then just like you saw before, right, we're going to have reductive elimination. So you can think about reductive elimination as, I know we mentioned it in the Heck reaction, but reductive elimination is basically where the palladium eliminates itself from being between the two carbons. So this palladium right now, I guess I should note here, this palladium is palladium 2, this palladium is palladium 2. So reductive elimination is the palladium eliminates itself from being between those two bonds, which means the two carbons end up bonded together. And then the palladium gets removed and reduced. So it goes back to being palladium 0. So we come over here, right? So we're here. We do the reductive elimination. We make our product. And we regenerate our palladium 0 to do oxidative insertion again, right? So that is kind of the whole catalytic cycle, right? So the transmetallation works pretty much the same for tin, magnesium, and zinc. With Suzuki reactions, they work a little bit differently, and they have a slightly different, more complicated mechanism. I know you're thrilled, but we'll get to that in a second. So hopefully, so far so good. Like I said, on Tuesday probably we'll have. I'll leave some time for some questions when we start, just so you can voice your displeasure with video me. All right, so click, click, click. There we go. So here's an example of not one but two Stille cross couplings. So here we have this every time, this, and this. So like what? Why did he lose his mind? Well, the 45th time the picture decided it was going to move, he lost his mind, right? So then that ends up being here and here. Oh my god. Oh my god. All right. So if you see there's two iodides here, and they were very fortunate that one iodide decided to react and not the other. One of my faculty members at the University of Pittsburgh was in the Nicolau group when they did this reaction, and he said that no one thought the reaction was going to work, and they actually thought that someone snuck in and put the product in the flask because they thought there was no way this would work. Good times. And so once they had this and they had this iodide, they did a second Stille reaction where then they took, we're running out of colors, took this, which is, I gotta find it, which is right there. Oh my gosh. And then we're gonna go gray. And then this guy here. Oh my gosh. I didn't even touch the screen that time. And that, okay, that, anyway. So then those two went together. So there are a few things that are different than things we've seen previously. And I'll point those out real quick. Other than the fact this molecule is huge and it's kind of miraculous that this worked, is first we have palladium DBA. I guess I should do it correctly. Palladium DBA. So this is palladium DBA. Chloroform adduct is technically what this is. And this is kind of not unique, but different than a lot of the other palladium ligands we've talked about, right? Because most of them we thought about where your palladium has, you've got like a phosphorus, right? And that phosphorus dumps oh gosh. So you've got your palladium, and then you've got like a phosphorus, and oh my gosh, I'm gonna have a stroke. And that phosphorus dumps electrons into the palladium, and that gets it to be a ligand. That's how it sticks together, right? But instead, here, DBA, I don't know why it gets to be red, is dibenzylidine acetone. And so this kind of works out that you have a DBA and with a palladium, a DBA with a palladium, and then a DBA. So that is palladium to DBA3. And then the chloroform adduct. You can get it with or without the chloroform, which, again, sometimes matters. It's just kind of like hanging out, like kind of trapped inside the structure. It's not like kind of in any one specific place as much as it's just kind of like trapped in the structure. So here, the palladium's just associating with these double bonds, and so it's not like as clear of a structure, or it's easy to see as a structure. And then we don't have phosphine as the ligand. We have arsenic. So arsenic is, I do believe, 1 under phosphorus on the periodic table. This is just super duper duper bad for you, phosphorus, right? But arsenic has different properties than what's it called? Than phosphorus, which can make it better or worse as your ligand. This one, in both of these, they also use a base. They use Hunix base. That's not necessarily needed, but it may have been that they found that their yields were better, or that they kind of got an improved. They might have been generating some acid some other way during the reaction, and so they found that adding a little bit of base helped mitigate that and got them higher yields. Especially with I'm like looking at my, go back here. So there you go. They used base, so Hunix base, here and here. So you can see like right here, this is an acetal. You may remember this from Organic 2. And acetals are not not stable to acid. So it could have been that if they generated any acid at all, so if there was a little bit of water in the reaction or something, that this caused this to fall apart, or this substrate right here is an aminal. So this O carbon nitrogen, that's called an aminal. And aminals are kind of like acetals, except for instead of an oxygen, one of the groups is a nitrogen, and those can be are not stable to acid as well. So there may have just been enough sensitive functional groups that they had to throw in a little bit of base to help mitigate any acid they might be generating some other way during the reaction. All right. So now Nagisa reactions are done with zinc, and the issue with Nagisa reactions is R zinc X. So aryl or alkyl zincs are not air stable. They're really, really sensitive to water. So while Negishi reactions work, they are much more difficult to do operationally because they have to be really dry, or you just don't get you don't have your zinc long enough to do the reaction. So if we look at this first reaction up here, so the first part of this right here, that is just making your aryl zinc that you need to do the reaction. So you've got your lithiated pyridine, and then you have your zinc. Again, trying to make it so you can read stuff. If I do that enough, you guys will actually be able to read things. Right, so I've got my lithiated pyridine, and then I add my zinc chloride. And so basically what happens is this attacks the zinc and knocks. You're screaming at me right now, I'm sorry. This attacks the zinc and knocks the chlorine off. I will give you a second to swear. All right. Now that you have that, now this right here is the metal side of the cross coupling. And so after the palladium inserts into this carbon halogen bond, then you can have then it will cross metallate with this zinc here. Not cross metallate, gosh, trans metallate. I just taught you that word. It's the COVID, man. I got that COVID brain fog. So, and then like you can see here, palladium DBA, no chloroform this time, and triphenylphosphine, no arsenic, yay. Then down here we have a very similar reaction, but right, we talked about this before. Step 1 is we had 2 equivalents of tert butyllithium, YOLO, no fear. And what that does, right, is that's going to do a lithium halogen exchange. We talked about these before. So that's going to make that iodide a lithium. And then once I have that lithium, then that reacts with the zinc chloride like we saw above. The lithium knocks off a chloride from the zinc and gets us to this structure here. And then this is what we cross couple with our iodide. So here you can see it doesn't always have to be an sp2 hybridized carbon. It can be sp3. Then we have Kumada couplings. Kumada couplings suffer from kind of the same problem as Negishi cross couplings, right? Is Grignard reagents. Are not air stable. So Stille reactions, you can just buy aryl tins and they're pretty stable. Negishi and Kumada cross couplings, you typically have to either make the organozinc or Grignard reagent when you need it, or for Kumada couplings, a lot of times you can just buy the Grignard reagent. Grignard reagents are pretty are pretty prevalent, and you can just buy a whole bunch of different ones. That does make it a little bit easier, but um, they're not something like you can just usually like keep for a long period of time without them going bad. Um, so here they were able to add this carbon right there. Oh my god. I don't know why sometimes it doesn't do it and other times it does. I don't understand. See, I don't understand. Um, so it adds those two together. And then down here, same kind of thing. We've got this guy here. I'm like trying super hard to not touch it to mess it up, and it just doesn't matter. It's like you will mess this up. So that is that right there. So that puts those two together. So, see here. So Stilly Pro, um, Pro is you have a stable starting material. You can just buy our SN, we'll call this R prime and R3, right? With you can buy tins with a bunch of different things. They're stable. You can put them in the fridge. You can put them on the bench, and they are going to be stable. The downside is tin is really bad for you. So I've been doing some Stille couplings in my lab. I try to make sure the scales are kind of small. If we do something big, I do it. I've seen enough in my life. So you'll notice that a lot of times for Stille reactions, it's going to be tributyl tin, because tributyl tin kind of is the right balance between what's the word I'm looking for? Safety and effectiveness. So trimethyl tin works way better for cross couplings because it's easier to get to the tin to do the transmetallation. But trimethyl tin, the trimethyl tin byproducts of the reaction are very toxic because they're easier to absorb. Tributyl tin works similarly to trimethyl tin in terms of transmetallation, but because it's bigger, it's harder to be absorbed, thus a little bit better for you. And then Nagishi and Kumada Pro, they're safe, right? Zinc and magnesium are fine. Con, not stable slash react with water. So those, while they're not going to kill you, they're really hard to use sometimes. Particularly Nagishi reactions are notorious for being hard to get to work. So, pros and cons. Pros and cons. It is what it is. Now, kind of the happy medium between the Stille and the Nagishi and the Kumada, where you have both stable starting materials and things that are safe, are Suzuki reactions. You see, I forgot to put the boron on this. I'm sorry. So here you have boronic acids, and those boron is non-toxic. These are, for the most part, pretty bench stable. You can just throw them on the bench and they're going to be there forever. And then you're able to do cross couplings. So again, same kind of thing. Here, oh my god. And here. And then, oh, we're going to pick a different color here. Blue. This. I didn't even touch it wrong. And that. Okay. So then that couples together. So let's take a second here and think about why the bromine that was coupled, right? Because there are two bromines. One, oh my gosh, and two. So why did we couple bromine 1 and not bromine 2? What's different about them? And what's different about them is their steric environment, right? Bromine 1 is trans to the rest of the chain, right? So you look at the double bond, bromine 1 is as far away from the rest of the chain as it can possibly be, where bromine 2 is cis to the rest of the chain. So for the palladium, which palladium is pretty big, to insert into the carbon halogen bond of bromine 1, that's easier than inserting into the carbon bromine bond of bromine 2, because when it does that, it's going to bang into the carbon, it's going to bang into that mom group, and all this stuff. And so that's why we react with bromine 1 and not bromine 2 in this example. And then down here, we have this protected sugar being cross-coupled with this molecule here. And you notice that all the examples that we have are really complicated molecules, or for the most part, they're really complicated molecules. So these cross-couplings are really key in how we build large, complex molecules, because they're all very selective for, like, I only react where there is a halide and a metal. And that's where I react, and that's it. Now, the Suzuki reaction has a slightly different mechanism. So, I guess I should point out here that boron is not a metal. I apologize. It's a metalloid. So if you look on the periodic table, there's where boron is, there's a line that does this down the periodic table, like aluminum's under it, where there are metals that touch that line have like metal and non-metal properties, so they're called metalloids. They're like mostly metals or kind of metals, and so boron kind of falls in that. So it's kind of the only example here that's not like truly like a metal. See, if I pause, I have to edit everything. I don't want everything. So I'm sorry, you'll just have to listen to me die just a little bit. Just a little bit. All right, so the beginning of the Suzuki reaction, exactly the same. I'm talking with my hands, like you can see. Exactly the same as what we've seen before. Palladium 2 goes to palladium 0 if you started with palladium 2. Then you get your palladium 0 that you either made or started with, and it gets ligands loaded onto it to make your catalyst. And hey, same first step, we do an oxidative insertion. Right? Amazing. Seems great. Right? Now, what is kind of unique about Suzuki reactions is Suzuki reactions have to have a base. Oops, try again. I don't know why I've lost the ability to write. There we go. Why do you hate me? They must have a base, and that base needs to be, oh, there it's back. Great. And that base needs to be R O M, right? Where M is gonna be, I'll go up here, like lithium, sodium, potassium, things of that sort. So, that base serves two roles. First, it does this metathesis step where it is replacing the halide on the palladium with OR, right? So it's replacing that that halide with an oxygen on the palladium. And then, more importantly, is a carbon boron bond will not do transmetallation. Just can't do it. But if you have your base can react with the boron to make a borate, and borates can transmetallate. So let's go over here, remind ourselves of stuff here. So if you remember, I'm just going to put random aryl group on here. It doesn't really matter. We're going to put a metal. We're going to make it OH. It doesn't matter if it's OH or O-methyl, O-ethyl, whatever. So if we remember, the boron is the weirdo of the periodic table, and so it only has 6 electrons around it. So boron always has an empty orbital. And boron loves reacting with oxygen, or making bonds with oxygen, more than pretty much anything else. So, the oxygen here will stuff itself in that empty orbital, and it will make so now the boron has a negative charge, and again, we know anything from Gen Chem. 8 means you have a negative charge, so and that your metal is kind of hanging on by it. So the boronic acid, which is what this is. Oop. I could probably pick a different color. Here we go. So this is a boronic acid. The boronic acid can't transmetallate. You can't get the palladium to replace the boron on that aryl group. But when you have the borate, it can transmetallate. So at this point, now you've got your palladium right? Now it'll do the transmetallation. All right, I'm not going to try to hide it. This is where there's a cut. So I was talking about we get the borate, and we're able to do the transmetallation, and then that gives us the aryl with our palladium and our aromatic ring with the ligands on our palladium, plus we get the boron with now effectively, in this example, 4 oxygens around it, right? So we get another borate, right? So when you do the transmetallation, what we had seen before, we go all the way back, back to the stele here we go. Right, when we do the transmetallation, we get a, with like a stele, Suzuki, a Kumata, you put the halogen from your palladium onto your metal when you do the transmetallation. And boron doesn't want another halogen, boron wants oxygen. So by putting this oxygen on the palladium, when we do the transmetallation, it gives the boron an extra oxygen. Now, I'm going to send this fixed slide out. There was a mistake over here that I fixed. So this probably looks a little bit different than what you saw just a second ago, but I'm going to send out the fixed slides for you. Anyway, so you have the palladium with the oxygen on it. You have the borate. You do the transmetallation. You now have this OR is this one right here. So here is presumably that one. And then this OR is that one there. And it doesn't really matter kind of what the two other R groups are on the boron. They're usually oxygens. And then that gets you to your complex that has the palladium between the group you want to add and your benzene ring. You do reductive elimination as we've done before. And you throw some ligands back on there. And you will get your product plus get your palladium with its ligands on it again. And you'll turn the catalytic cycle over. All right. Now, some things to know, right? So you see a lot of, say, aryl. These are boronic acids. So having the boron with 2 oxygens on it is a boronic acid. Boronic ester follows the same kind of convention, right, as carboxylic acid and ester, right, and get rid of OH, make it OR. Boronic esters will also do Suzuki reactions, but what oftentimes will happen is you'll have like base, like sodium hydroxide, and they will, in the process of the reaction, turn into boronic acids. So the ester is kind of a like happy place where it can hang out. Oops. OR. I'm sorry. OR. So the So the ester might be a little more stable, might have some other attributes that you want, but oftentimes it has to be turned into the acid to actually do the cross coupling. In terms of bases, you have a lot of hydroxides, simple alkoxides, things like this. The counterion, again, matters, but like from first principles, it's hard to know which one's going to be best. But lithium, sodium, potassium, and then thallium gets used a lot. Thallium methoxide, I think both of our examples that I had used thallium methoxide, this hydroxide. So thallium is really good at doing Suzuki reactions. The problem is that thallium is super duper bad for you. So it's one of those things that's like you kind of go through all of your normal metal, all your normal counterions, and then you'll oftentimes use thallium as kind of like the counterion of last resort. Um, but yeah, your bases are normally hydroxide, and then lithium hydroxide, sodium hydroxide, those kind of things are what you usually work through. So not too much there. So we had talked about this with the other ones. The Suzuki, like the pros, it doesn't have many cons. Right? It's safe, it's stable. Right? So boron's not bad for you. It is the starting materials are stable. The con is you have to use a strong base. So if your compound's not stable to base, you are not going to be able to use these conditions. But in terms of just like the things you care about, like is it safe? Are the things stable? Can you buy them? Yes to all of that. It's just, does my compound like being around strong base? If the answer is no, the Suzuki is not your cross coupling. Now the Sonogashira is a cross coupling that you don't start with the metal on the compound. So what is different about the Sonogashira than everything else? First, you use a terminal alkyne. Right? So you have a terminal alkyne as your starting material, no vinyl metal or anything like that. And that's really the big one, is you are starting out with this hydrogen on the end of your alkyne. I don't know why this doesn't have like the actual starting material. It is this. Right? And you are doing your cross coupling. But you don't have the metal, so where does the metal come from? So when you have an alkyne, well, a terminal alkyne, copper really likes the electrons of pi bonds, double bonds and triple bonds. And so with a terminal alkyne, you will have the copper will associate with or coordinate to the pi bond. And when it does that, it makes this hydrogen more acidic. So when you have like triethylamine or any other kind of trialkylamine base that normally wouldn't be able to deprotonate a terminal alkyne, with the copper bound to it, now that hydrogen's acidic enough, and you can make your copper acetylide, and this is your metal for transmetallation. So you're making your metal compound in solution. So if we go back here, we look at the mechanism. So there are two different ways that we can make the palladium 0 if you start with palladium 2. One is the way that we've seen before, where you have your palladium 2. It reacts with either your phosphine ligand or your amine, and it will, gosh, words are hard. It will reduce it to palladium 0. Or you make your copper acetylide, and then your palladium transmetallates that, and then it does a reductive elimination to make this dialkyne, and then that gets you to palladium 0. It doesn't matter which path you choose, both are possible. It just matters you get to your palladium 0, slap some ligands on it, and then you get in the catalytic cycle. Thankfully, first step, always the same. It is a oxidative insertion. You insert into a carbon-halogen bond again. And then once you have that, that is where down here you make your copper acetylide. So that's that step we just went over. Copper associates with the alkyne, and then triethylamine or any trialkylamine base would protonate it. I have copper X here. The vast majority of the time, it's going to be copper iodide, but it could be another copper source, but like the vast majority of the time it's copper iodide. Then this does your transmetallation. It gets your palladium 2 with the alkyne on one side and the aromatic ring on the other. It does reductive elimination and gives you your product. And then gets you back to your palladium 0. So these are really handy reactions. There are kind of some cascade reactions where you can make words are really hard, where you can make indoles. So what we saw over here, if we go back, right, they make this alkyne, and then they treat it with this gold reagent. The gold really likes the pi bonds of an alkyne. It makes it so the nitrogen can add to make an indole. So these are quite handy reactions to make these alkynes. So with all that, hopefully this all makes sense. And we'll go over some stuff on whatever day that is. Tuesday? Yeah, there we go. Words are hard. We'll go over stuff on Tuesday to make sure that everyone's kind of on the same page. And I'll answer any questions that you have about this lecture. I know it was a lot to do not in person, but I couldn't have us missing effectively 3 days of class between hurricane and COVID. So I wanted to make sure that I got you guys something. And like I said, we'll catch up. So if you have any questions, just write them down and I'll make sure we get to all of them before we keep trucking along. So, all right. I'll see you guys later.